if you look at the other projector, the J here is the projector resulting from a composition of the Rother-Dexter operator and the derivation. So E is 1 minus J. So J is the other guy, the complementary guy. Then it has this kind of description. It's also a kind of Rother-Dexter type operator, but a different axiom. I mentioned this one, that the C is a subring of F, whereas the I is an ideal. The image of the integral operator is an ideal, and you have these various ways of integration by parts. We have this direct sum, okay, and I mentioned this also in the morning. This standard example of smooth functions is where the I would be the ideal of functions satisfying the initial condition at the origin. In the case of an ordinary integral differential algebra, it turns out that you can describe the full family of possible Rother-Dexter operators corresponding to the derivation in terms of the characters. So every character on your algebra F corresponds to exactly one integral, namely the integral whose evaluation is this phi. And that's a bijective correspondence in the ordinary case. So now, to do actual computations, we need a description of the operator ring. And we want to really do these computations in Maple with the operators. So it's like when you do, it's now a kind of generalization of the Weil algebra, but also having these integrals inside. But it's all linear operators. So that describes the family of linear operators that you can write in terms of the derivation and the integral. And of course, the multiplication operators from a coefficient ring. And also characters. Okay? So what I do is I take the algebra, the K-algebra generated by my D here, which is now just a symbol. Here it's just a symbol that stands for the derivation. Another symbol for the integral, and then for every element of F, or more precisely it suffices to take a K basis of F, I take a corresponding symbol to denote the multiplication operator, and this F dot here just means the collection of all characters, all multiplicative functionals on F. So I take this as kind of variables or indeterminates, and I look at all the non-commutative polynomials that I can write in terms of these indeterminates. And I have to factor out certain relations, and these relations just tell me how these various basic operators interact with each other. Okay? And most of them are really immediately recognizable, so that's the Leibniz axiom that says if a derivation applied after a multiplication by f, then you just do this. And this here is just the Rother-Dexter axiom written as a rewrite rule now. Okay? So you have to imagine that this acts on another function g. So you have here integral of parenthesis open, f times the integral of g, parenthesis closed, is equal to that. That is here the differential Rother-Dexter axiom. So you see it corresponds to a different rule in this rewrite system. And the section axiom, that just says that if you apply a character, then you certainly get the constant function. So then afterwards doing a differentiation will give you 0. Okay? This just means that the character is multiplicative, etc. And this here is a Gröbner basis, a non-commutative Gröbner basis. So it's one of these instances where you have a confluent rewrite system. So this means that for those who don't know here, that even though in many situations you will have a choice of which rule you want to apply, in the end it doesn't matter because it all flows together. That's what confluence means, right? It all flows together into a unique, irreducible element where you cannot apply any other transformations anymore. That's confluent, and it's also the case that this never leads to an infinite reduction chain. So it's an Ethereum and confluent rewrite system. That's equivalent to being a Gröbner basis in this setting. Okay, and the nice thing is that not only do we know that there are unique normal forms, because it's a Gröbner basis, but we can also describe them explicitly, right? Namely, it turns out that every integral differential operator, so that's how I call these guys here, this operator ring, every integral differential operator can be written uniquely as a sum of a differential operator, an integral operator, and an element of what they call the evaluation ideal. So that's the two-sided ideal generated by the characters, yeah, by the multiplicative functionals on F. Yeah? And this ring here, it's a non-unital ring, because otherwise this wouldn't be a disjoint decomposition. Yeah? That's simply the unital ring that is generated by taking here just the integral and the f's and modding out, I mean, you only need to mod out that one, okay? And of course that one. Okay? That's the ring of integral operators. So you can write it as a unique sum of these three components, which in a nutshell really tells you that this is good for boundary problems, because in a boundary problem, you're given a differential equation, which is an element here. You're given boundary conditions, which are written elements there, and the solution is a Green's operator, is an integral operator. So the solution is described by that. So it has all the things together. And it turns out that this evaluation ideal can also be described as a left module. So this here is the ideal. I always have to think left or right. This is the right ideal, yeah? The right ideal generated by the characters, yeah? Intuitively, this just means that you can do whatever you like, yeah? But in the very end, you have to apply a character, yeah? And this means you get down to a number, yeah? Because you evaluate at some point, yeah? That's the right ideal of generated by the characters. And then if you take linear combinations with factors of f on the left-hand side, then what you get is exactly this two-sided ideal, this evaluation ideal. That plays an important role. Okay, and this exactly this right ideal generated by the characters, this plays also an important role in the applications, because that's what is called the Stieltjes conditions otherwise. Yeah? In the normal forms, it's easy to recognize what they do, because in the normal forms, they are all linear combinations of elements of this form and elements of that form. Yeah? This one here, these are local conditions, and these are global conditions. So, for instance, yeah, in the standard setting of C-infinity functions, this would be a typical Stieltjes condition. Okay? So this here on the left-hand side, that's a local condition, doesn't involve integrals, it just involves, it could also be u prime of 1, yeah? It just involves point evaluations and derivations, nothing else. Yeah? There's local conditions here. But the other one here, integral from 0 to 2 psi squared u of psi, that's a global condition. That's something that you can write in this form. Yeah? And Stieltjes conditions are just whatever can be written in this form. So the normal forms under our rewrite system really break down into these components, but algebraically they are just the right ideal generated by the characters. And the reason why we introduce them is not so much because of applications, because to be honest, there are not that many applications. Yeah? There are some problems like heat transfer, when you have Stefan Boltzmann condition for radiation or something, then there is an integral turning up. But that's rather the exception. So they are not that important. But for us, they are important because they come naturally when you take a boundary problem and you factor it. Yeah? And even if your original problem did not have any Stieltjes conditions, the factor on the left-hand side will generally have a Stieltjes condition. Yeah? So we need them. Yeah? We need them for this reason. Yeah? And also you saw they pop up in the algebraic description of the normal forms. Yeah? So when you look at the two-point boundary problem, then this is a very special case that is covered here, and it's exactly the case when you have only two evaluations. Yeah? So instead of all these characters that can evaluate at various points, you just choose two, left and right endpoint. Yeah? That's why it's called two-point boundary condition. So just two evaluations, and you agree that you don't use any integrals. Yeah? And normally, when you look at boundary problems, you will see that the order of the boundary conditions is always strictly less than the order of the differential equation. Okay, these are the three assumptions. Yeah? That's not necessary for uniqueness or existence. Yeah? It's just necessary so that the Green's operator is a continuous operator in terms of the natural topology. Yeah? But algebraically, that's not something that is really necessary. But anyway, yeah? In the 2-point boundary conditions, you have these 3 conditions, and then it turns out that you can use a nicer structure to describe this. This is what I had in my original JSC 2005 paper. You then have just 2 integrals. The integral initialized at L, and the integral initialized at R, left and right evaluation points. And these 2 operators are then adjoint with respect to this inner product. So the a plus f morally is a definite integral from 0 to 1, and the inner product just integrates, that should be f times g, sorry, f times g, the product of f and g is operated on by a plus b. And then they are adjoint there, and the canonical case is a is the integral from 0 to x, and b is the integral from x to 1. So it integrates, so to say, the rest of the integral, and they are adjoint to each other, and they are actually also adjoint in the Hilbert space setting, because if you extend this to the L2 functions, then these will be actually adjoint operators in these topologies. But here it's completely algebraic, and it's just this bilinear form. Okay, now I can make the definition of a boundary problem a bit more concrete. I defined it already as something that is a surjective linear operator and a subspace of the dual. But now I impose the further condition that this T here is a monic differential operator with coefficients from F. So from the first component of this operator ring. And furthermore, the boundary space is generated by Stieltjes conditions. So these are all the functionals that I can write down in this language. These are the Stieltjes conditions. So I require the boundary space to be generated by such Stieltjes conditions. In that setting, I can do computations. I can do everything algorithmically. So that's what I call concrete boundary problems. And again, they form a submonoid, which is very natural. Because whenever you multiply something which is described within this language, then what comes out is again described in this language. And a regular boundary problem will have the consequence that, in particular, the order of the differential equation must correspond to the number of boundary conditions, or the dimension of this space. It's of course not sufficient, but this is a necessary condition. And of course, you can use the matrix test that I showed you before. And again, the regular concrete problems, they are again an even smaller submonoid. And we should distinguish this from so-called well-posed problems. That's something maybe I will discuss a bit later tomorrow. Well-posed means more than regular. Regular means just existence and uniqueness. And well-posed means that in addition to that, the solution should also depend continuously on the data, on the forcing function. That's stability. So Jacques Adamar introduced these 3 conditions for a problem to be well-posed. And algebraically, I don't see this part. I see it only in the sense that the order of the boundary conditions must be smaller. Then I will have a well-posed problem. Otherwise, it may only be regular, but not well-posed. Okay, and now the main theorem for this part is that if I'm given a fundamental system of the kernel of T, a basis of the kernel of T, then for any boundary problem in this sense, I can compute the Green's operator in this operator ring. I have an algorithm that gives me a representation of this Green's operator. And in the case of 2-point boundary problems, with these 3 conditions that I showed you before, it turns out that the Green's function, whose analytic definition is in terms of this Dirac deltas, etc., this Green's function really corresponds bijectively to the normal form of G. And it's a trivial exercise to just write the Green's operator in terms of a Green's function. We'll maybe show you an example. It's really the same thing. The normal forms of the Green's operator, they are the Green's functions. But of course, the Green's operators are much more general, because if I have global conditions, etc., then you cannot write it with the Green's function, but you still can write G as a normal form. Okay, so here, again, this example that I showed you before. So written as a boundary problem in this language, I write it as this pair. The kernel projector can be written down here, just using the formula that I showed you earlier. It's again an element of the operator ring, of course, that's the projector. And the Green's operator just means, as I showed you before, you take any right inverse, well in that case it's trivial, yeah. What's the right inverse? Yeah, you just multiply 2 times by a. Yeah? So a squared is a right inverse, and if you just use all the rewrite rules, then this is the normal form that you get for the Green's operator. And now you see how you get the Green's function. Yeah? It's very simple, yeah? Because the a is an integral from 0 to x, and the b is an integral from x to 1. Yeah? So that corresponds to the case distinction that the terms with the b, they come into integral from x to 1, so that means psi is greater or equal to 1. Yeah? The elements with the b come into the lower case, and the elements with a come into the upper case. Okay? And the x to the right of the a becomes xi here because it's integrated, and the x to the left it's just an x because it's multiplied after the integration. And so it's a trivial rewriting from Green's operators to Green's functions. And of course, yeah, you can also compute the state operator here, the dependence of the solution on the boundary values, rho and sigma. But for ODEs, this is a trivial exercise. Yeah? But for PDEs, this is far from trivial. Yeah? So semi-homogeneous problems are only interesting in the PDE case. Okay? So here's an example with a third order differential equation. So in classical notation, you write it like this, some third order equation here. And I give 2 boundary conditions at u and at 0, and in addition, first derivative of 1 is 0. And here the Green's operator will look like that. And again, you can write it as a Green's function. Okay? And that is somehow interesting because we realized that Maple has a rather ad hoc support for boundary problems, because when you enter this into Maple, it will not be able to compute this. Yeah, I didn't try out the newest version, but the last time it didn't do it. Huh? But if you change the boundary conditions a little bit, sometimes it comes up with a solution. And it's not really predictable when it works and when it doesn't. Yeah? It's somehow rather ad hoc that it tries to adapt the integration constants in some magical way, which sometimes works and sometimes doesn't. Yeah? But in that case, it didn't. Okay? So also the factorization that I showed you earlier is also something that can be made algorithmic. So the simplest example is this u double prime is equal to f, u of 0 is 0, u of 1 is 0. And what I told you before is that even we had no global parts in the boundary conditions in the big problem, in the left factor they turn up. And it's always the left factor, because the right one will be a subspace. The boundary space will be a subspace of the given one, so it will be a subset of the boundary conditions or linear combinations of it. So only here something can happen. But if you use an initial value problem, of course, if you use here u of a is equal to 0 and u prime of a is equal to 0, then you will just get u of a equals 0 here. You will not get the global condition. But for a true boundary problem like here, you do get it. Here's another example, just taken from Kamke's collection. So I prefer to write it usually for presenting in this traditional notation. So u 4 prime plus 4u equals f, and 0 and first order conditions. And again, you see it's just a bit more complicated, but the principle is the same. On the left-hand side, you get global conditions for the left factor. Global conditions, the right factor is simple. And again, you could choose different conditions here. You could choose, instead of u of 0 equals 0 and u of b equals 0, you could maybe choose u of a equals 0 and u prime of b equals 0. Then this will still be the same here, because the left factor is uniquely determined. Okay, so should we make some break here, or should I go through the full talk as you prefer?
Maybe take 5 minutes. Mm-hmm.
Because I think it's a bit heavy. Or this, it's maybe reconvene. Because now it's a natural transition.